All right, today we're diving into something, well, it's a bold idea, and I mean really bold. It's called the time force hypothesis, and it's a pretty wild attempt to fix one of the biggest problems in all of science, and maybe, just maybe, create a single theory of everything. So let's jump right in.
So everything we're about to talk about, it all comes down to this one kind of mind-bending question. We usually think of time as something that just happens, a result of all the laws of physics playing out. But what if we've got it completely backwards? What if the steady forward flow of time is actually the fundamental engine that drives everything else, creating the laws of physics as it goes? Just keep that in the back of your head.
So why do we even need a crazy new idea like this? Well, because, let's be honest, modern physics has hit a bit of a wall. There's a huge fundamental problem right at its heart, and that's really where our story has to begin.
Okay, so you've got our two greatest hits in physics. On one side, you have general relativity. It's beautiful, it describes the big stuff, like planets and galaxies, in a smooth, elegant way. Then on the other side, you've got quantum field theory, which describes the tiny, chaotic, and frankly weird world of particles. Now, here's the problem. They both work perfectly, in their own lane. But when you try to get them to talk to each other, they're totally, fundamentally incompatible. And one of the biggest sticking points is time itself. It just doesn't mean the same thing in these two theories. It's a house divided.
And that's where the time force hypothesis, or TFH for short, steps onto the stage. It comes in and says, hey, what if you're all starting from the wrong place? It suggests a completely new fundamental rule for the universe, one that doesn't start with particles or fields, but with the one thing we all experience constantly, time moving forward. At the very core of this whole thing is one incredibly simple idea. The TFH proposes that this is the one and only master law of the universe, that everything that happens, literally everything, is just energy flowing to reduce some kind of imbalance. It's just trying to find equilibrium. That's it. Seriously. The claim is that everything else we see just follows from that one principle. And this, well, this is what that super simple idea looks like when you write it down in the language of math. Now, don't worry, you don't need to be a mathematician to get the gist of this. Think of it less like a scary equation and more like the master recipe for how the universe works. Let's just look at the two main ingredients. Okay, so this first chunk of the equation, it's actually pretty standard stuff. This is a classic wave equation. Physicists have seen this a million times. It's great at describing how stuff like light waves, or really any kind of energy, moves and spreads out through space. So far, so familiar. But this part, this is the game changer. This little addition, this alpha term, that's the secret sauce. It's what's called a dissipation term. All it does is force everything in the universe to lose a tiny bit of energy over time to kind of run down and calm down. It makes things irreversible. This little term is the arrow of time, baked right into the most basic law of nature. Okay, so if that one little equation is the only rule in the entire game, how in the world do you get a whole complex universe out of it? I mean, how do you go from a simple energy flow to, well, everything we see? Let's see how that's supposed to happen. Yeah, that's the big question, right? If the universe is fundamentally just one big energy field, this phi thing from the equation, and all it wants to do is chill out and find balance, then where did all this stuff come from? Space, time, electrons, all of it. And the answer is this really cool concept called emergence. So imagine the entire universe is just this one giant cosmic pond of energy. Space and time, they aren't separate things. They're just the properties of the pond itself. And what about particles like you and me are made of? Well, they're just stable little whirlpools that last for a really long time. And gravity, that's just the big, slow, large-scale current of the whole pond. See, everything we know just emerges as a different kind of pattern in this one underlying field. All right, now for the really cool part, the payoff. You see, a theory of everything isn't just an intellectual exercise. To be worth anything, it has to actually solve the problems we're stuck on. And the TFH makes the bold claim that it can neatly explain the two biggest puzzles in cosmology right now. First up, dark energy. That's the name we give to whatever's causing the expansion of the universe to speed up. The standard view is that it's some kind of mysterious anti-gravity force, but nobody knows what it is. In the TFH view, though, there's no new mystery force needed. The cosmic acceleration is just the universe as a whole,
relaxing. It's the large-scale effect of that universal energy field running down and dissipating, just like the master equation says it should.
And then there's dark matter, the invisible glue that seems to be holding galaxies together. For decades, the standard view has been that it's some kind of new particle we just haven't been able to find. But the TFH says you can stop looking because you'll never find it. Why? Because it's not a particle at all. It's just a persistent warp, a gravitational distortion in the energy field itself, caused by all the regular matter sitting there.
And that is the absolute beauty of this idea. Suddenly, you don't have two completely separate, baffling mysteries that require two brand new, unknown things to solve them. In this picture, dark energy and dark matter are just two sides of the same coin. They're just two different ways we see the same single universal process, energy flowing toward balance. Okay, this all sounds pretty neat, maybe even elegant. But look, a cool story isn't science. For any of this to be taken seriously, it has to be testable. It has to make real-world predictions that we can go out and check, predictions that could prove the whole thing wrong.
So we have to ask the big question, the question that separates real science from just a nice bit of philosophy. Can we actually test this thing? Does it make specific predictions that we can either confirm or, falsify?
And the answer, according to its proponents, is a huge yes. This theory gives physicists and astronomers a literal checklist of things to go look for. For example, it predicts that gravitational waves from things like black hole mergers should lose a very specific, tiny amount of energy as they travel across the cosmos, something our detectors might be able to spot. It also predicts a very precise shape for the dark matter halos around galaxies that powerful telescopes like the JWST can go and measure. These aren't just vague ideas, they're hard numbers. If we look for these things and they aren't there, the theory is toast.
But here's what might be the most powerful part, the real kicker. All of these different predictions, from tiny quantum effects in a lab to gravitational waves to the structure of entire galaxies, they are all connected by a single number. And that number is just the Hubble constant, the rate the universe is expanding today. That's the alpha from the master equation, one number to rule them all, so to speak.
So it really all comes down to this. The idea has been proposed, the math has been worked out, the predictions have been made, the ball is now in the court of the experimentalists and the observers. The test now passes from theory to observation.
And that leaves us with this one last kind of wild thought to chew on. For centuries, physics has looked for its deepest truths in ideas of perfection, symmetry, and things that last forever. But what if the ultimate secret, the law that gives rise to absolutely everything, was hidden in the most simple, everyday observation there is? The fact that a hot cup of coffee, left on its own, always eventually goes cold.